All right. Hello, everybody. Welcome to our next round of fellows intro talks. First is Kyrylo.
Yes, that's correct.
So, Matthew, you want to introduce it?
Yeah, so Kyrylo is we're very happy to have him back because he's actually done an IRIS-HEP fellow in the past, which was great. So he's joining us now to work with me as well as Lucas, Heinrich, and a few members of the CERN team, Marcin and Mario, to try and help improve Rucio, which is a software technology that is used extensively by Atlas as well as other experiments to try and make it compatible with S3. So without any further ado, I'll let Kyrylo take it away.
Thank you, Matthew. All right, so the project is called, well, basically Rucio S3 compatible access interface. And I guess first I'm going to just break down what the name stands for. And the first is, of course, Rucio. And as Matthew said, it's an open source data management software. It's really widely used in high energy physics, also like at CERN, because it's very data intensive, the project, so there has to be a way to manage that. And Rucio does scalable data management, because that's like the main problem of large experiments at high energy physics projects. It also helps with data replication. Data can be duplicated and stored at multiple locations for redundancy and improved performance. Then data is distributed through different storage endpoints, ensuring that data is available all the time and accessible to scientists and collaborators. And of course, the provenance, so information about its origin, history is stored, and things like that to make sure it's gonna work fine. So now I'm gonna talk about the S3 interface. So first about the S3, it translates to simple storage service. And this is basically a cloud-based object storage service provided by Amazon. Quite simple. It's lightweight and easy, scalable, and actually really widely used nowadays for various applications such as data backup, archivation, content distribution, data lakes, and many other things. And that's why it's a really nice portable way to share some experiment data as well. So the goal of this project is basically to make a bridge between Rucio and S3 to allow users to manage S3 buckets right from the Rucio interface. All right. The imagined capabilities of this project, basically a command line interface with some code in the backend. We want to extend Rucio to have like a command like S3. Then you'll be able to make a bucket with the following syntax, even though it's actually a bit different in the S3. It's not dots and colons, it's slashes. So that's like the first thing I have to somehow solve. Then we should get the credentials from Rucio, export them to then be able to use different clients to access the same S3 bucket. So not only from Rucio, but also from something like MC, which is a Minayo tool, external S3 client, basically. Of course, like copying files from using MC and then accessing them using Rucio. So that's main goals of the project, basically. Now, a bit about progress and timeline. So currently, I'm in the 3rd week. I've been exploring Rucio, reading through some source code to understand what parts I will have to change, exploring possible ways to handle the authentication, going through S3 API. Then next couple of weeks, I'm gonna be trying to implement some basic data transfer capabilities between Rucio and S3. Then integration testing, because as I said, we want to support different storage backends, not only the CERN S3 instance, but also the Minayo and things like that. Credentials extraction is, of course, some additional features in the following weeks. Access sharing, quotas. We want our buckets to be writable by specific users or members of selected experiments. Sharing files with other teams, quota of manageable objects. And then in the end of the project, I'm gonna just close the GitHub issues I opened in the first place, refine the documentation that of course has to be written for the project, and work on the final presentation. As you can see on the timeline, I'm kind of in the beginning, and then the final date of the project would be September 22nd. All right, and well, that's it from my side. Because there was an empty slide before. Interesting. Yeah, thank you very much for your attention. I hope I did it in 5 minutes.
Yeah, that was fine. Are there any questions? For Kyrylo? No? All right, good job. Andrii, you're up next.
Yeah, maybe I can also make an introduction for Andrii. So my name is Petro Zarytskyi. I'm representing CMS, and in this case, we are talking about study of data popularity in CMS. It's also related to the Rucio project. Like, we're still adapting it in CMS and learning how to use it to its full potential. And so here we are doing a study to see if we can predict long-term access patterns based on various information that we have in the system. And so it goes a bit beyond of what normally is done in Rucio. Andrii is doing it, I think it's his second fellow with IRIS-HEP. And first time he was doing some machine learning for QCD background suppression in one of the experiments at LHC. And now it will be also about machine learning, but more for data management.
Hello, my name is Andrii Len. I'm from Taras Shevchenko National University of Kyiv. My project is predict CMS data popularity to improve its availability for physics analysis. My mentors are Dmitro Kovatsky, Rahul Chauhan, and Hassan Ostuk. CMS data management team is responsible for distributing data among various computing centers globally. However, due to limited disk space on these centers, it becomes necessary to dynamically manage the data available on disk. When data is not readily available on disk, users have to wait for it to be retrieved from permanent tape storage, causing delays in data analysis and hindering scientific productivity. In order to perform analysis, we need data about data usage, which will be taken from the CRAP archives. CRAP, short for the CMS Remote Analysis Builder, is a utility to submit CMS SV jobs to distributed computing resources, and it also allows general users to access CMS data and Monte Carlo and exploit the CPU and storage resources over there. We will use Spark Analytics cluster on Swan to take and proceed our huge data. After taking data, it is crucial to identify relevant features or characteristics that can help predict data popularity. Here is an example how from a single name of data set we can extract 3 features such as primary data set, acquisition era, and data type. There are much more features which we will take directly from CRAP database and investigate them. To gain actual results, we need to consider current and historical trends of datasets usage. It is possible due to the fact that every time when a user trying to access some dataset, the timer of his request, which is called a task, is also stored in the CRAP database. Also, one of the most important challenges of this project will be to find the right machine learning model, which can make time-dependent connections. For example, we can use recurrent neural networks, which are effective for sequential analysis, or transformers, especially those based on the self-attention mechanism, like the transformer architecture. A typical question that we want to answer is, will the data set be accessed in the next months? And to answer this question, we need to take data. Data should include which data sets are accessed, when they are accessed, the frequency of accesses, etc. This data will serve as a training set for our machine learning models. And then we will perform feature engineering. The features could include variables such as the size of the data set, the historical access patterns, the type of data, or any other relevant metadata associated with the data set. Then we will search for an appropriate machine learning model to train on the collected historic data and predict the popularity of data sets. Then we will evaluate the model. This step ensures that our predictions are reliable and can guide data management decisions effectively. After all these steps, we can integrate the developed tool into the existing CMS data management infrastructure so that it can continuously monitor and update data popularity predictions. Currently, I'm working on the first three steps simultaneously because it's hard to understand each one of them appartly. So I need to work simultaneously on three of them. Thank you for your attention.
All right. Thank you, Andrii. Any questions for Andrii? Okay. Up next is Mykola.
Hi, I'm Mykola Kolomiiets from Taras Shevchenko National University of Kyiv. My mentors are Petro Zarytskyi, German Giraldo, and Jen Eisermans. The title of my project is Improving Testing Procedures for Prompt Data Processing at CMS, and the system responsible for this is Tier-0 Tier-0. It has some other responsibilities, so all of them are workflow configuration, output data placement, prompt reconstruction of the data, and bookkeeping for the most sensitive data in the CMS experiment. Here you can see a scheme of data flow from storage manager to Tier-0 and how it handles the data. Currently, there are two types of tests in use in Tier-0, Python syntax tests and Tier-0 replay. There also are some outdated unit tests. They are not currently in use, and they are not currently in use. This is a table to see the difference between multiple different types of tests. Python syntax tests are very quick in execution, obviously, and don't require much computing power. So we execute them for any pull request. But the only type of error it can find is syntax error. And there is also the full integrational test, or also known as replay. It creates Tier-0 operational conditions. So it requires much time, high amount of computing power, but we can find all types of errors, just like in production. It runs before every deployment, so we know for sure we don't lose any data, because Tier-0 is responsible for prompt data processing, and it's important we don't lose any important data. So we have this gap between those tests. They are very different in scale. One is very quick in execution and don't require much power, and the other is very heavy, very consuming in time and computing power. And we want to remove this gap by developing unit tests and small functional tests. So it would be easier for developers to find out the state of their code. They wouldn't need to run replay to know if there are some unit errors or some other errors that can be found with small functional test. Ideally, a small functional test would be like a replay, but smaller and would require much less computing power, and we would like it to run locally, so it would be easier for developers. I have been working for the project for 2 weeks now and made some changes. Here you can see my first pull request. I added inject limit parameter to tier-0 config, so we can limit the number of limit sections inserted into the system. And limit section is a basic unit of data in CMS. It corresponds to 23 seconds. So we can limit inserted data into the system. And how did I do that? I just modified SQL query, so it returns only limited amount of limit sections. In this example, only 10, and it make possible to run a replay much quicker. So this is my project. Thank you for listening.
Thank you, Mykola. Any questions for Mykola? I see two of your mentors are connected. Dmitry or Jan, you want to say anything about the project?
No, not in particular. I think, yeah, the scope is clear because we clearly lack this flexibility of having smaller tests at tier 0, and Mykola already implemented these first changes that we can greatly use already from now on. So it's going well so far, and we hope to see much more development in the next weeks. So very nice. Great, thank you.
Petro, you're up next.
Cool. So my name is Petro Zarytskyi. I'm from Taras Shevchenko National University of Kyiv in Ukraine. And my mentors are Vasil Vasilov and David Lench from Princeton. And my project title is Optimizing Reverse Mode Automatic Differentiation with Advanced Activity Analysis. So I would like to start with a bit of an introduction of what automatic differentiation is for those of you who might not know. Well, basically, automatic differentiation is a method of differentiating a function that is expressed as a procedure. So that might be a function that expressed as some kind of C++ code, let's say, as in this case. So what we do to automatically differentiate a function is we basically break it up into smaller elementary operations, and we apply chain rule to each one of them. Obviously, we could do that from the start to the end of the function. So basically apply chain rule from the input values to the output values of the function to compute the derivatives. Or we could do it the reverse way. So go from the output values to the input values. The second approach to go like the reverse way turns out to be more efficient for the cases where the number of inputs is bigger than the number of outputs. So, for example, computing gradients. This is the method that my project focuses on. Okay, this method includes 2 passes, so basically a forward pass and a backward pass. We need a forward pass to compute all the intermediate values of all the variables, and a backward pass to compute the derivatives. Okay, so now a bit on what CLAD is. CLAD is a tool that is used for automatic differentiation in C++, and it's implemented as a Clang plugin. So what it does is Clang is a C++ compiler. So what CLAD does is that it takes Clang AST, so it's the code that is converted to a abstract syntax tree. It takes that code of a function that we want to differentiate. It automatically creates the corresponding Clang AST that represents the derivatives of that function and adds it to our code. So like a huge advantage of CLAD compared to, let's say, TensorFlow or other tools like that is that CLAD is not domain specific, which means that we don't have to write code specifically for CLAD. We can just use our existing C++ code and that would work perfectly with CLAD. Now a bit about activity analysis. What activity analysis is? Well, basically, activity analysis comes down to analyzing the code of the function and deciding if we need some kind of variables or we don't need some kind of variables. So whether we need to store them or whether we don't need to store them. Some of the examples of activity analysis might include derivatives. So we might not need to store derivatives of variables that don't depend on input values in a differentiable way, or we don't need the derivatives of variables that don't influence the output values in a differentiable way. So those would create basically just dead code. And there are other examples of activity analysis that could be implemented that you can see right here, but I'm not going to focus on that probably. A significant type of activity analysis that I'm focusing on right now is called to be recorded analysis, and it basically means that, well, as I said, in reverse mode automatic differentiation, we have to do two passes. So we create, so we first do the forward pass. So we go from the input to the output, and we compute all the intermediate values of variables that we use to, in that function. And well, on this diagram, let's say we have some variable x. So first we declare it, then we change it in some way. So do some kind of assignments or something, and then we use it to maybe compute some kind of other expressions and so on. Blindly, what we would do with in automatic differentiation here, we would store that variable every time that we change it. So before we change it, we always want to store the intermediate value of that variable. However, this is not always necessary because we don't have to store, for example, in this example, the value of that variable before it was changed right here, because it's never used before that expression. So we don't need the value of that variable before that. And there are other examples like that where we can actually not store some variables. Like right here, we can look at the program and notice that k does not depend on x or y, so the arguments of the function. So we actually never have to store the derivative of k. So, and if you look closely on this example right here, you can notice that the derivative of k just basically produces dead code. A similar thing happens here. So here k does not influence the return value in a differentiable way. So here the derivative of k produces lots of dead code as well. So that's why we need activity analysis. We needed to analyze the code before creating the derivative and not create some unnecessary variables. By the way, this code was automatically created by CLAD, so this is quite representative. Basically, my goals for this project is first, find the best optimizing strategy for CLAD and implement it. Then after that, investigate the potential of the Clang static analysis and data flow analysis infrastructure to capture advanced optimization opportunities. So yeah, and then investigate the possibility of enabling CLAD in AD bench infrastructure, and then test CLAD in major workflows like routes, proofit package, and basically do basic things like writing new tests and new documentation for activity analysis tools, and in the end create a benchmark to compare the efficiency with activity analysis on and off, so to figure out how efficient that is and how much it really helps to improve the efficiency of the code created by CLAD. So this is it. Thank you for your attention. Do you have any questions?
Matthew, go ahead.
Hey, thanks for this nice talk. This is really interesting work to see. So you had mentioned, yeah, on the slide that you're looking at incorporating this into RECAST, which is obviously fantastic. So thank you in advance. I guess I was under a misconception from discussions with Vasil that RECAST already had, at least in development, automatic differentiation support in it. So did I misunderstand, or is CLAD going to enhance that?
To be honest, for this moment, I focus just on activity analysis itself, and this is just a thing that that my mentors pointed out that would be useful to do in the future. So I'm just going to like investigate the potential of that. Like right now, I'm just thinking about like the strategy for activity analysis itself.
Yeah, okay, cool. All right, thanks very much.
All right, any other questions? Okay, and now Andrii.
Yeah, maybe I can introduce
Okay.
Andrii. So yeah, so Andrii is a fellow who's working primarily with myself and Lukas Heinrich. So I won't kind of give away the full extent of his project, but as people might know, Lukas Heinrich is the original creator of the first implementation of the RECAST, I guess, methodology or strategy. And during that timeline, he created one workflow language backend for it. And so Andrii is looking at using Snakemake to extend the possible workflow languages. So without any additional information, I'll let Andrii take it away and explain the rest.
Yeah, so hi everyone. My name is Andrii Povsten. I'm doing this year my IRIS-HEP summer fellowship with Matthew Fikert and Lukas Heinrich. And the theme is the Snakemake backend for RECAST, implement the Snakemake backend for RECAST workflows. So to ensure the reusability of any data analysis, this analysis, they need to be archived in a way that allows them to be easily rerun. And RECAST was implemented for such purpose. RECAST is a framework for extending the impact of existing analysis performed by high-energy physics experiments. And this framework allows scientists to access to reuse workflows that have already been performed. And as Matthew mentioned, the current backend for RECAST is the YEDIC. YEDIC is workflow management system, which basically represents our workflow as a direct acyclic graph, which I will show you in the next slide. And also the Rihanna, it's just a reproducible analysis platform that allows researchers to run containerized data analysis in the remote computer clouds. And this Rihanna, firstly, the RECAST can be integrated with Rihanna cluster. And yes, and Rihanna also worked on the YEDIC, and as we will see later, the Snakemake. And first, I just want to show you the example workflow with YEDIC. As you can see, if you can see my mouse, it's like this code basically, and you can it contains all the scheduler. The scheduler it's basically describes the logic, how our nodes and the edges are built for our graph, and it contains of the dependencies which are described of then the scheduler should be applied. And so our project is to switch basically from the YEDIC backend to the Snakemake backend. So the Snakemake is a framework for reproducible data analysis. And it provides a lot of cool features, but the main motivation why people thought about switching from the YEDIC to the Snakemake is that because that's the first that the RECAST was implemented, there wasn't any mature Linux containerization workflow language. So as Matthew mentioned, the YEDIC was created, which basically, as you can see, it can set our container and or Docker image. And but nowadays the Snakemake supports containers, and Rihanna can also be Rihanna also communicated with the Snakemake. So why we choose Snakemake is just for all the solutions because it's Python-based workflow management system, so it's easy to read. I will show you next slide some small piece of code. And it's a tool that's used widely in the broad scientific source community for the large-scale data analysis, and it supports widely used and robustly supports for contributors from all communities. And as you can see, it's just this. So basically, the Snakemake creates the snake file. As you can see, the first image is this. I just wrote a small program where you can see the basically Python script. This program just take the input text file and count the words, how many words in this text file, and then write the result in the output file. So as you can see, it's just easily to read, I hope. And yes. So the key objectives for this project is to, as I mentioned, is create a new backend for RECAST with the same YEDIC functionality. And then we want to verify that these Snakemake workflows are compatible with Rihanna Snakemake workflow engine, and then test what's more efficient to use the Snakemake or the YEDIC. So yeah, and so now on my on time schedule, I'm basically trying to run the same run. Try to rewrite the same YEDIC files for RECAST examples on the Snakemake.
Thank you, Andrii. Any questions for Andrii? No. Okay. All right. Well, thank you all for your, thank you all of the fellows for their presentations. We look forward to seeing how your work finishes up. Thank you to all the mentors who attended and for any other guests that are here. So thanks. That's it for today. So.